invitation. Yeah, my pleasure to be here today. And a little bit of information about myself. Again, I'm here with TU Delft since the beginning of last year. My research area is scalable graph learning, and I'm also teaching a course on scalable learning systems, master's course. Please consider taking it if you are still taking master's courses. That's in Q4. And before that, I was with IBM Research for 15 years, more or less. And I worked on a variety of different topics. In the last 6-7 years, I was working on data and AI systems. I was a senior scientist, and in my last 3 years, I was basically leading a research challenge, global IBM research challenge on graph machine learning for financial crime analysis, and I'm mainly covering that work in today's talk. And right after me, Çağrı Bilgi is going to give a talk about the continuation of that work at TU Delft. We have made some more significant advances in this field. And so, as I mentioned, in the last couple of years at IBM, I worked on enabling AI in financial transaction processing, especially detecting financial crime. And this work actually became a product in towards the end of 2023. You might be familiar with IBM's mainframes, right? They have been around since 1950s. So the latest reincarnation of IBM's mainframes are these Z series processors. Does anybody know what Z stands for? Zero downtime. So these machines are optimized for transaction processing, and they can keep running for years without failing. That's why financial institutions, governments, etc., heavily use these machines. And you probably used an IBM Z machine today, if you have used your credit card, because 90% of the credit card transactions still go through these machines. And of course, the machines have been redesigned several times over those 70 years. And the latest reincarnation of Z machines, Z16 machines, also support some advanced AI capabilities, both at the hardware level and at the software level. So at the hardware level, there is an on-chip accelerator for fast inference processing. So the transactions can be processed at very low latencies in real time. So you can classify transactions in real time. At the same time, there is a software stack that runs on top of it, which is called IBM's AI Toolkit for IBM Z and Linux One. So that's what we have contributed to. So we built some graph machine learning capabilities within this AI toolkit, which enabled real-time transaction monitoring to detect, for instance, fraud or money laundering, various different types of financial crime. Okay, so also this work was partly supported by the Swiss National Science Foundation under this project, and also it led to a PhD thesis done by one of my students, Jovan Blanusa, who had several publications. And also last year in 2023, he won the Best Industry-Related Doctoral Thesis Award in Computer Science in Switzerland. So I have to acknowledge his hard work. Our work also led to an IBM Outstanding Accomplishment Award for the contributions to System Z. And let me talk about some of the trends in financial crime analysis before I go into the technical details. So first of all, the standard way of dealing with fraud or AML is to use rule-based systems. In particular, for AML, the financial institutions, anti-money laundering, the financial institutions rely heavily on rule-based systems, but these systems are being replaced by more agile, AI-based systems. And the financial institutions are required to implement know your customer and customer due diligence mechanisms. So they have to know about their customers, And if the regulators request this information, they have to make it available. So with all that additional data that comes into play, we now have to follow the data instead of just following the trail of the money, right? So the knowledge graphs, AI, etc., all of these are coming together. And the banks also see a need to unify AML and other financial fraud detection solutions to reduce the costs, basically, instead of having to maintain multiple different solutions, just one solution that can be tuned for different needs. And here the challenges are basically the criminals are constantly coming up with new crime patterns. So we have to be able to have mechanisms that can detect constantly evolving crime patterns, and we have to do it fast, right, to minimize the damage. And the criminals, actually criminal networks can spread across many banks and across different national boundaries. So you need to have a system that can deal with that. Of course, the resulting system has to be cost efficient and sustainable, right? So you don't want to use infinitely many resources, and if it's too expensive, it will discourage the financial institutions from taking advantage of these technologies, right? And then there are also all these regulatory compliance, trustworthy, and secure AI issues, right? So, but in this talk, we will be focusing mainly on detecting constantly evolving crime patterns in real time. Okay. Let me start with an interesting example. So this is a cluster of accounts and transactions between those accounts extracted from the Ethereum blockchain. So this is real data, and it's also labeled. So you see that the phishing accounts are labeled in red. Yeah. So actually, some hackers really kept track of the email traffic of phishing scams and identified the phishing account IDs and labeled them on the Ethereum blockchain. So we took this data and we looked at it a bit, right? So this is essentially a financial transaction graph in some sense. You have accounts and transactions between different accounts. And you see some interesting patterns here, right? So these phishing accounts, obviously, they are trying to collect money from their victims. So you see lots of transactions sending money into these accounts, right? So you see a very high fan-in here. And then you also see these phishing accounts, right, sending money to some intermediate accounts, right, which are not usually visible, right? So they are not part of these phishing emails, but they are probably the mules carrying money, right, between different phishing accounts. So account holders that are cooperating with the scammers, or they might be accounts also owned by the same scammer, right? So there are these accounts, and you see many transactions towards those accounts, right? So a very high fan-in, a very high degree out, but a low fan out, right? So only one receiver. So this is an interesting pattern, and we see the same thing here for this phishing node. And we also see some interactions between the two, right? And then we see the same behavior here. Here we also see some small cycles. So the money is returning back to the same account, right? So visiting an intermediate account and returning back. So there are some interesting patterns in this graph, right? So now let me ask a question. So what type of graph is this when you look at it? There are some cycles actually in it. So first of all, it's directed, right? And then second, it's a multi-graph. You can have multiple different edges between the same two nodes. So there can be multiple different transactions at different points in time between the same two accounts. And these transactions might be associated with like different timestamps and different amounts and things like that. So this is a directed multi-graph. This is something that we have to keep in mind. It will come back again. Yeah, and you see, this is a really important problem we are facing today. I myself have been a victim of a phishing scam very recently. On a Saturday morning, my wife woke me up and she told me we received a message from the tax office, Belastingdienst, which said we had an outstanding payment which had to be paid immediately, otherwise we would get a fine. And she showed me the website. It looked familiar, and I said, okay, why don't you pay it? I don't think we have an outstanding payment, but I will call them later and figure it out with them. And we paid it, and it turned out that the message wasn't from the Belastingdienst. And yeah, so also the website was fake, and we basically paid to a criminal. So I became one of the victim nodes here, and my money is now traversing this network. It's very hard to get it back. So it's only a few hundred, 300-400 euros, if I remember correctly. And we went to the police, and they basically they can't do anything about it, they say, because the amount is too low, right? It's only a few hundred euros. And so, but these guys are doing it at a very large scale. So at the end, who knows how much money they are collecting from their victims, right? So something has to be done about it. And obviously, my bank is not using the IBM solution. Where is it? Yeah, so they are not using our AI toolkit. If they were using my AI toolkit, for instance, they could identify the fraud in real time, block the transaction, and save me some money. Right? So anybody can fall victim to this anytime, I think. I mean, you are not fully awake, and you can make a mistake very easily. And there are no repercussions as far as I can see. So we need our banks to take advantage of these advanced AI technologies. And this is another example, money laundering, right? So the money laundering is the process of injecting illicit funds into the financial system and disguising their origin, right? So you mix the illicit funds with licit funds, disperse these funds in the network, etc., so that the financial authorities, regulators, etc., cannot discover the origin of the money. So the guys, criminals, scammers who stole my money, right? Basically, they withdraw it in the form of cash, for instance, and they have a shell company that they are working with, a front company, seemingly looking legal. It could be, for instance, a laundry business, right? So they give this money to their friends who cooperate with them, and the money itself gets dispersed into several different accounts after having been mixed with some licit funds, and then they end up in perhaps another criminal account, which then integrates the money into the financial system, right? So here, right, so the illicit funds enter into the financial system in the placement stage, and then we see some layering activities, right? The money is scattered across multiple different accounts and then gathered again. So this is where we start seeing some patterns in the data, crime signatures in the form of some graph patterns, right? So this is how we can actually detect this type of money laundering events. And the thing is, these patterns are similar across many different financial crime techniques, right? So money laundering or phishing scam, you do see some similar patterns. And here are some known suspicious financial transaction patterns. For instance, money leaves one account and returns back to the same account after visiting some intermediate nodes. High fan in and high fan out. This is what you see with scammers. Scatter gather patterns, one way of mixing illegal and legal funds and hiding the origin of the illicit funds. And the money could be, for instance, shuffled between some input and output accounts. So this is known as a by-click pattern. This is known as smurfing. And so the thing is, if we can capture these patterns, right, we can significantly improve the accuracy of financial crime analysis. So on the left, you see the financial transactions in a tabular format. So each row here represents a financial transaction. You can see the source bank ID, source account ID, amount, currency, payment type, etc. for each transaction. And here on the right, you see the graph representation where the nodes are the accounts and the edges represent the transactions between different accounts. So here you see when this transaction takes place on 7th of July between the accounts D and A, if we were able to discover that this transaction actually completed a temporal cycle pattern in our financial transaction graph, we could capitalize on that information to make much better predictions about our financial transactions. So if you simply train a tree-based model, for instance, light GBM, on this type of data, by the way, these data sets are typically very highly imbalanced. The illicit transaction rates are less than 1%, even less than 0.1% typically. And so if you train a tree-based model on this tabular data representation using the original transaction features, you get an accuracy of basically minority class F1 score of around 9%. However, if you do this additional graph analysis and discover that, for instance, this transaction actually is part of a cycle, it completes a cycle, and use it as an additional pattern, for instance, add an additional column to this table and train a tree-based model on the extended table, you can improve the accuracy significantly. So this is quite important. And then once we do that, basically here you can see how the transaction features are extended using graph patterns, for instance. We can count the number of cycle patterns of length 3, 4, and 5, etc., and add additional information into the feature vectors. Once we do that, right, also we can explain the decisions, the predictions made by our machine learning models. Especially if you are using tree-based models, they are known to be more explainable than neural network-based models typically. So you can also do some feature importance analysis and see which features actually contributed most to the prediction, right? So you can say that the amount was, I don't know, around $1,000, and this transaction was part of a cycle, so that can be used as an explanation. I mean, in my case, right, so the phishing scammers, they are typically probably asking for a few hundred euros, and they are collecting money from lots of victims. Again, that's another signature, right? So a high fan-in and the amount between 300 and 400 euros, right? So this is what I think a bank should expect, and it shouldn't be too difficult to discover, in fact. Okay. And then actually, let's look at these results in some more detail and what they mean for us, right? So here we see the true positive rate versus the false positive rate. Here the true positive rate is basically the recall, and false positive rate is basically the 1 minus precision, right? So the thing is, for instance, if we fix the true positive rate at 60%, right? So you see two different curves here. The purple curve shows the trade-offs we get when we use only the raw transaction features, and the red curve shows the results we get when we use also the graph-based features. So we see that at the same true positive rate, right, of 60%, we can reduce the false positive rate by almost 80%. So this is very important for banks. Why does it matter? Of course, if we are talking about anti-money laundering, a higher true positive rate means less regulatory risks. So you capture more events and you are less likely to receive fines from regulatory authorities because you miss them. In case of fraud detection, of course, you minimize the damage to your customers, right? To me. So, and in case of what does lower false positive rate means? It means, again, more cost savings for the banks, right? So the bank personnel has to do less work to analyze the false positives. I mean, let's look at the confusion matrices a bit. We understand what's going on a bit better. So these are the results that we obtain on this data when we use only raw features. And these are the results that we get when we use also the graph features, right? So the true positive rate is fixed to 60%. And you see what is happening to false positives, right? So actually, this is a 100x reduction in the number of false positives obtained by banks. So it's very important to achieve a high accuracy when we do this type of analysis. Okay, so let me see how much time I have. Okay, good. So at the end, this is a summary of the solution that we built in IBM's AI toolkit for Z, right? So the input is a set of financial transactions, a batch of financial transactions. These financial transactions go through a combinatorial analysis layer called a graph feature preprocessor, which searches for different types of patterns, known suspicious patterns, and maps them into some feature vectors. And then we build, we use some standard machine learning techniques on top of them, typically gradient boosted trees. They are known to be very effective on tabular data. And this part is also mapped to this special AI inference unit, which enables us to do predictions in real time at very low latencies for small batches of transactions. And this part runs basically on the CPU, graph analysis part. But it can also run in real time, and it adds a very minimal latency to the pipeline. So we optimize the implementation of these algorithms in such a way that they can operate on very small batches, and they can exploit the very fine-grained parallelism that are part of the combinatorial exploration process. Okay. And yeah, so what's next, right? So we talked about a two-step process. And what is the disadvantage of this two-step process? Of course, you have to know about the patterns that you are looking for, right? You have to do some feature engineering and feature extraction, explicit feature extraction. You need domain experts who know about the fields. And this first part, basically the graph mining algorithms that we are using, these are not differentiable. So this is combinatorial exploration, right? So we don't have an end-to-end differentiable graph machine learning approach here, right? Can we replace this two-step process with a single-step process based on graph neural networks? That's the question we have explored afterwards. And of course, the advantage of graph neural networks is they can basically operate on top of the raw transaction features. You don't really need to do explicit feature engineering. And they can also discover unestablished patterns simply by looking at a few labeled transactions, right? And they are also differentiable. So you can connect graph neural networks with transformers, large language models, etc., in an end-to-end differentiable pipeline to do more interesting things. So does it work? Yes. So Benny Agresti was a PhD student from ETH who did a 9-month internship with me at IBM back in 2023. And he did quite some interesting work on top of these financial transaction graphs. So one thing important that we have to keep in mind is that these financial transaction graphs are directed multigraphs, and this is very important. So if we simply take a standard graph neural network and apply it to our financial transaction graphs for instance, age classification, transaction classification, or account classification, node classification, we don't really get very promising results. So one has to take into account some of the peculiarities of these financial transaction graphs. First of all, they are directed, right? We talked about the importance of, for instance, computing both the fan-in and fan-out, degree in and degree out, right? So you have seen the Ethereum phishing example. So if we only do like reverse message passing in the forward direction of the edges, we can only compute the in degree or fan-in, right? We can only compute the in degree. If we would like to also compute the out degree, we need to receive messages from the destination neighbors. So we need to do message passing also in the opposite direction, in the reverse direction of the edges. This is what we call reverse message passing. So you do forward and reverse message passing at the same time. And then these are multigraphs, right? So there can be multiple different edges between the same two nodes. And you would like to be able to distinguish between the edges that are originating from the same node and the edges that are originating from different nodes. For instance, this helps you when you compute fan-in and fan-out. So here you see the degree in is 3, right? But the fan-in is 2. So if you assign some port IDs to some of these edges, then you can actually compute the fan-in and fan-out correctly, right? So, and there are also other considerations. This is not only about fan-in and fan-out computation. And then if you would like to be able to compute the cycle patterns, you need to add ego IDs. So your, let's say, origin node has to broadcast its ID to its neighbors. And if the message comes, returns cycles back to it, then you can actually discover that this node is part of a cycle, etc. And then another important thing is that these financial transaction graphs, I mean, the financial transactions are edges in our graph, and there are lots of attributes, edge attributes we can take advantage of. So if we do edge updates, in addition to node updates, we can significantly improve the accuracy. And we also did some theoretical analysis and showed that actually combination of some of these adaptations makes the graph neural network provably powerful or universal, and makes it possible to detect any directed subgraph pattern in multigraphs. And here are some of our results. So these are the results that are obtained using IBM's graph feature preprocessor. So here we combined Light GBM and XGBoost with IBM's graph feature preprocessor. So they were trained on graph features in addition to the original transaction features. And we evaluated these models on 5 different data sets, 4 AML data sets, small-sized, medium-sized, small-sized around 3 million transactions, medium-sized around maybe 30 million transactions, and with high and low illicit rates. Basically, high illicit rates means 0.1% illicit ratio. Low means 0.05. But you see actually a significant drop in the accuracy. I mean, when that you have fewer illicit examples you can learn from. And ETH is the Ethereum phishing dataset, phishing scam dataset. And these are the results obtained using IBM's graph feature preprocessor in combination with tree-based models. And these are the results we obtained using our graph neural networks with multi-graph adaptations, which we refer to as multi-GNN models. An important thing to keep in mind is that, of course, here the graph features are used. Here, the graph features are not used. The graph neural network models have been trained directly on the original raw transaction features. So the feature discovery was done implicitly within the neural network layers. And we obtained that multi-GNNs outperform consistently the more traditional approach without any feature engineering. And we have also run some additional tests to actually highlight that they are in fact capable of detecting some of these suspicious graph patterns. So, and yeah, so what's next? We would like to extend this approach to do graph learning on relational databases. We are not the only ones that are looking at this problem. So from Stanford and from Amazon, some groups are working on similar problems. The idea is that, of course, as I mentioned, the banks have to implement know your customer and customer due diligence mechanisms. So they have to know about their customers. They have a lot of information about their customers. For individual customers, it could be rather limited. So a driver's license, a passport address, and things like that. But for companies, they have a lot more information. Right? So business licenses, partnership agreements, etc., etc. So in addition to our financial transaction graph, we have all this information, which can be stored in the form of some node or edge features. Some of this information can also be text-based, right? So basically, we have text, we have tables, we have graphs, and how do we combine all this information to do more accurate predictions on data sets with several different tables, right? So relational databases and tables. So that's the idea. That's one thing we are looking at. And of course, another far-reaching goal of our research is basically to be able to build, let's say, foundation models for financial fraud detection. Of course, the input data will be a combination of graphs, relational tables, text, etc. You would like to be able to build a single model and fine-tune it for different tasks, right? This is another way of saving costs for banks, right? So they don't have to maintain a different software library or software tools for all these different fraud types, but build just one model and then fine-tune it, right? So you also don't need lots of domain experts that know about all these different fields. Of course, if you can learn from a limited set of labeled examples, then how do you do the pre-training, how do you do the fine-tuning, etc. These are all very interesting problems. And of course, another advantage of domain-specific models is, again, they can be more compact and accurate for that particular domain, and that also reduces the operating costs. So in this talk, I mainly discussed the challenges related to detecting constantly evolving crime patterns in real time. Çağrı will say a few more things about that. And there are other challenges that are yet to be answered. And for instance, finding criminal networks crossing banks and national boundaries requires cooperation between banks as well as regulatory authorities. One needs secure multi-party computation and decentralized learning techniques, differential privacy, etc. And one has to build cost-efficient and sustainable AI technologies. I referred to domain-specific foundation models, but one can also do things about, developing more efficient hardware and software. Regulatory compliance, trustworthy and secure AI are other issues, right? So you can take advantage of large language models, etc., to improve the accuracy, but are they compliant with the regulations? And vice versa, of course. And you have to be able to explain your solutions and make sure that your solutions are fair. Of course, we are not looking into these problems. I know there are others in our department who are working on some of these topics, so it's great. And of course, open models, hybrid cloud, how do you do private fine-tuning? These are also interesting challenges. That's all from me. I'll be happy to answer your questions.